In this problem, there is a small puck of mass, small m, which is carefully placed onto the inner surface of the thin cylinder. The mass of the cylinder is capital M and its radius is capital R. Initially, the cylinder rests on the horizontal plane and the puck is located at the height R above the plane, as you can see in this picture. We have to find the interaction force, capital F, between the puck and the cylinder at the same moment when the puck passes the lowest point of its trajectory. Here, we assume that the friction between the puck and the inner surface of the cylinder is absent and the cylinder is also rolling and it moves on the plane without slipping. It means it has the pure rolling condition. And obviously, the free fall acceleration is g. Here is the solution of our problem. As you can see in this picture that when the puck reaches the lowest point inside the rolling cylinder, there would be a net force, that is F minus mg, which works on the puck, and it provides the centripetal acceleration toward the center of the cylinder. Here mg is the force on the puck due to gravity and F is the contact force from the cylinder on the puck, and this contact force is the interaction force which we have to find out. So at the bottom point we can write it F minus mg is equal to m into centripetal acceleration. Here we are taking the upward direction as positive. Now, because the cylinder is also moving, so in this case the centripetal acceleration must be calculated by using the relative velocity concept. That is, the velocity of the puck relative to the center of the cylinder. And let u is the velocity of the puck at the bottom point of the cylinder and v is the velocity of the center of the cylinder. So it can be written as v relative is equal to u minus v, that is u plus v. Here we are taking the rightward direction as positive. So we can write our equation as F minus mg is equal to m into a square of v relative upon r. Here a square of v relative upon r is the centripetal acceleration of the puck. Now we have to focus only on v relative, that is, we have to calculate individually the velocity of the puck at the bottom point and the velocity of the center of the cylinder, and you would get our answer. So let us begin our journey. Now let us consider the puck is at an angle theta inside the cylinder, as you can see in this picture. For now, our purpose is to focus only on the horizontal motion of the system. As in the case of the puck, we can see from this diagram that the horizontal component of the normal reaction N is the one who is responsible for the puck's horizontal acceleration. So we can write it as an equation form that mass of the puck into Ax is equal to n sine theta. Here Ax is the horizontal acceleration of the puck. This is our equation 1. Now we focus on the horizontal motion of the cylinder. On the cylinder, there are two horizontal forces which acts. The first is n prime sine theta, which is the horizontal component of the contact force exerted by the puck on the cylinder, and the second is frictional force, which acts opposite to the direction of the motion of the cylinder. So by taking the direction of the motion of the cylinder as positive, our horizontal equation would be n prime sine theta minus force of friction is equal to mass of the cylinder, that is capital M, into W. Here W is the horizontal acceleration of the center of the cylinder. As you can see in this picture that n prime and n are equal in magnitude. This is from Newton's third law. We may write the equation as n sine theta minus force of friction is equal to mass of the cylinder into W. Here n prime is replaced by n, and this is our equation 2. Now we focus on the rolling motion of the cylinder, and since the cylinder is rolling without slipping, that is it's in the pure rolling motion. And as you can see in this picture that the frictional force is the only force which produces torque on the cylinder. As we can see that as far as this normal force n prime is concerned, it acts along the radius, and therefore it can never produce torque about the center of the cylinder, and thus would not contribute in its rolling. So we can write the torque equation for the rolling condition of the cylinder, that is torque is equal to force of friction into R. And as we know that the torque is the product of the moment of inertia and the angular acceleration of the rolling body. So we can write it as I into alpha. That is, I is the moment of inertia of the hollow cylinder and alpha is its angular acceleration. So the equation would become I into alpha is equal to force of friction into R. If we put the value of moment of inertia of the hollow cylinder, that is mr square, and since it is pure rolling condition, then we can put the value of alpha as W by R, where W is the horizontal acceleration of the center of the cylinder. So after substitution, it would become m into R square into W by R is equal to force of friction into R, and we get the value of force of friction, that is mass of the cylinder into W. This is our equation 3. Now if we substitute the value of force of friction in equation 2, we would get 2 into mass of the cylinder into W is equal to n sine theta. This is our equation 4. And again, from equation 1 and from equation 4, we would get m into ax, that is the mass of the puck into acceleration of the puck in horizontal direction, is equal to 2 into mass of the cylinder, that is capital M, into W, that is the horizontal acceleration of the center of the cylinder. This is our equation 5. And after integrating the equation 5 with respect to time, and since at the initial stage the system is at rest, you would get mass of the puck into U is equal to 2 into mass of the cylinder into V, and this is our equation 6. Now we would apply the energy conservation law on the moving system, and as we can see in this picture that as the puck slides down, it losses potential energy. This is equal to mgr. Here m is the mass of the puck and r is the radius of the cylinder, and this energy becomes kinetic energy of both the puck and the cylinder at its lowest point. So we can write it as a small m, that is the mass of the puck into g into r, is equal to kinetic energy of the puck at the bottom point, that is half into mass of the puck into u square plus kinetic energy of the cylinder at this moment, that is half into capital M into v square plus the rolling kinetic energy of the cylinder, that is moment of inertia into angular velocity square, and this can be written as mgr, that is mass of the puck into g into r, is equal to half into mass of the puck into u square plus half into mass of the cylinder into v square plus half into mr square. This is the moment of inertia of the hollow cylinder into v by r to the whole square. This is the value of omega, and as we know that for the pure rolling condition v is equal to omega r, so we can substitute the value of omega as v by r here. Hence we get the mass of the puck into g into r is equal to half into mass of the puck into u square plus mass of the cylinder into v square. This is our equation 7. Now by solving equation 6 and equation 7, you would get the value of u, that is 2 into root under capital M into g into r upon 2 into capital M plus small m, and also we would get the velocity of the center of the cylinder, that is v. This is equal to small m divided capital M into root over capital M into g into r upon 2 into capital M plus small m. In this way we can get the relative velocity of the puck with respect to cylinder at the lowest point of the motion of the puck, and this relative velocity would be equal to u plus v, and if we put the value of u and v, then you would get 2 plus small m by capital M into root over capital M into g into r upon 2 into capital M plus m. And this is our relative velocity which produces centripetal acceleration on the puck toward the center of the cylinder, and this centripetal acceleration is square of the v relative upon r. Now we come our final force calculation. As we can see in this picture that at the lowest point the forces on the puck are in the upward direction is interaction force or contact force, that is capital F, and in the downward direction that is the weight of the puck, that is small m into g. So at this moment the force equation would be F minus mg is equal to m into v relative square upon r, that is F is equal to m into square of the relative velocity upon r plus mg. It can be written as F is equal to small m into in bracket g plus square of the relative velocity upon r, bracket close, and if we put the value of v relative in this equation, then you would get the value of F, and this is equal to F is equal to 3 into small m into g into in bracket 1 plus small m upon 3 into capital M, bracket is closed, and this is the required interaction force between the puck and the cylinder when the puck is at the lowest point of the inner surface of the hollow cylinder. This is our answer.